Hello and welcome to this revision session for AQA A-Level Physics Paper 3. So in today's revision session what we're going to be looking at is how we can understand the different practical skills needed for Physics Paper 3A in AQA A-Level Physics. So if we've been successful and we've learned in today's lesson, we'll be able to understand what the different practical skills are for AQA A-Level Physics, assess our understanding on practical skills needed for AQA A-Level Physics, and finally understand what practical skills we need to improve upon for AQA A-Level Physics. So in this lesson we're going to look at the following parts of the specification, looking at the idea of independent thinking, the use and application of scientific methods and practices. Now overall, at least 15% of the marks for all A-Level Physics courses require the assessment of practical skills. Now the majority of these marks for AQA are found on A-Level Physics Paper 3A. Now in order to be able to answer these questions you need to have been taught and have acquired competency in the appropriate areas of practical skills as indicated in the coverage of the table below. So things like independent thinking, the use and application of the scientific method and practices, numeracy and the application of mathematical concepts in a practical context, and instruments and equipment. Now like GCSE there are several required practical activities, 12 separate experiments you must have carried out and understand the processes behind. But unlike the GCSE qualification, questions are not likely to be based on these practical activities, rather based on the skills you acquire in them. So therefore it's important to build your competency in each practical skill so that you can apply this to different applications in different experiments. So let's have a look at experimental methods. Now it's a common exam question to ask students to write an experimental method or to derive a particular set of values or a value. So to carry out this task what you should do is split your response into three sections. The first section is looking at the independent and dependent variables. So you should be identifying the independent variable and the dependent variable. State how each variable will be measured with the correct measuring device, and then state the range and interval of the independent variable for this investigation. Now always remember that the range of the independent variable must be as large as possible while still being safe to carry out the experiment, and that the experimental range is the set of values for which the conclusion, the trend and the values are valid for. Now the interval of the independent variable should be at least 5 values for the dependent variable. So this would allow for a line of best fit and a trend to be established easily with the data that you have accrued. Now the second section is all about experimental technique. When you're discussing your method you've always got to talk about identifying any control variables and how you will control or monitor them. Identify any way the experimental technique can be modified to reduce any uncertainty, and discuss carrying out repeat measurements and calculating averages if appropriate. Now always remember, measurements should be repeated until concordance is achieved with the value, so you're getting approximately the same value each time with your repeat. Now repeated readings until consistent results or concordant results are achieved reduces the random error of the results. The last section you've got to discuss about in your method is the graph. So in your method you've got to state the graph that will be drawn from the experimental data gathered. Now if you need to derive a value from the graph, look at ways the y-axis and the x-axis values can be adjusted to get a straight line of best fit. Then you can put the experimental equation into the form of y equals mx plus c and work out the calculated wanted values. So remember, if you're asked to write about an experimental method, state the independent and dependent variables, discuss the experimental technique, and highlight the graph that you would draw and what value you would gain from that graph. Now when you're writing your answer, split your answer into paragraphs addressing each part of the question. Now it's likely that the experiment will not have been an experiment carried out in class, so that's to be expected. Don't expect to be asked a question of writing a method on an experiment you've already done. You need to apply your understanding to different situations. Now using any information given in the question will help you structure your answer. So when you're considering an experimental method, think about the following things. Does the method actually test what's being asked to in the question? Is the method clear enough for someone else to follow? Apart from the independent and dependent variable, what are you controlling and how? Are the apparatus and techniques appropriate for what is being measured, and will they be used correctly? Will the method give precise results, i.e. will you get repeats with very little variation? Are repeat measurements needed to be taken in this particular experiment, and is the experiment going to be conducted safely and ethically? Now, when I've looked at feedback from previous examination questions, this feedback has been given from AQA examiners. It says that students should be encouraged to describe how to change one variable and to give suitable ranges of values, as well as specifying how many sets of results to take. It's also expected that students will describe graphical methods of processing results, including, where relevant, the significance of intercepts and gradients. Now, to gain credit for suggesting repeated measurements, students must be specific about which readings they're going to be repeated and mention averaging of those measurements. Now, it's been said that in these types of questions, students have found it harder to describe the way in which a suitable range of a set of results could be obtained, and very few mention the advisability of taking repeated values. Now, it should be noted that general statements like saying results should be repeated and averaged are not likely to attract a mark. So you've got to be particular about which measurements should be repeated. Now, as well, you need to indicate that if a graph is a straight line, you've got to indicate that if it goes to the origin as well. Now, many plans for these types of questions lack details on how to vary the independent variable and how to record the value of the dependent variable. Now, many students don't know how to process data to obtain a straight line graph, so think about how you would do that. Now, examiners insist on seeing that the dependent variable was either read or measured or recorded, and these are terms that examiners expect students to use if there are similar questions coming up on papers. Now, students can give an expression to show how their gradient could be manipulated to obtain a value, but examiners are expected for a value to be the subject of the particular expression, so always rearrange it and make the value that you want the subject of your equation. So let's have a look at an example question where you could be asked to write an experimental method. So, describe how you would use a circuit to determine accurate values of EMF and internal resistance. You should include the following details in your description: the measurements you would make, the range of values of the independent variable, how you would process and analyze your results to determine EMF and internal resistance, and how you would ensure the accuracy of your values of internal resistance and EMF. So what you should be doing is addressing each point with a separate paragraph in your answer. So each of the bullet points should be answered in a separate paragraph. Ensure you state which quantity you're going to measure and which quantity you're going to vary in your investigation. Remember to make it clear that you're going to take at least 5 different sets of the dependent variable by varying the independent variable. Clearly state how you will vary your independent variable, and clearly state the range and interval of your independent variable in your investigation. Now, if it's necessary, state any experimental procedures which would minimize experimental uncertainty with good experimental technique. And if possible, state how you'll repeat your experimental values until concordance is achieved, then an average is calculated. Now, this is done to reduce the random error and decrease the absolute uncertainty of your experimental results. Remember to state what graph would be drawn from your experimental values in your investigation, then how you would extract the wanted values from your graph. So as you can see here, we've got a model answer. So construct an electrical circuit with the power pack, ammeter and variable resistor in series with a voltmeter in parallel with the power pack. Turn on the power pack to 10 volts. Alter the variable resistor so that the current is 0.5 amps and measure the potential difference across the power pack with the voltmeter. Repeat this until results are concordant and calculate an average. Carry out this investigation for 0.5 amps, 1 amp, 1.5 amps, 2 amps and 2.5 amps and measure the appropriate potential difference. Draw a graph of the potential difference on the y-axis and current on the x-axis and draw a line of best fit. EMF is the y-intercept and internal resistance is the negative gradient of the line of best fit. So when looking at your mark scheme, you can see you've gained all 5 marks here by talking about how you extract the values from the graph, what graph you would draw, what range of values you're going to take, what measurements you're going to take from the circuit, and repeating and average any measurement. So let's now have a look at the ideas of errors. Now there are two main types of errors in investigation: systematic errors and random errors. Now systematic errors are errors which cause the same uncertainty in the experimental results, whilst random errors cause different uncertainties in your experimental results. So systematic errors affect the accuracy of your result, while random errors affect the accuracy and the precision of your results, the spread about the mean. Now both of these errors will affect the absolute uncertainty of experimental values. Now to reduce a percentage uncertainty, you've got to use larger values for your experimental results. So to reduce percentage uncertainty as well, you've got to use a measuring device with a greater resolution. Now there are two main type of examples here for your systematic and random errors. Your systematic error is a zero error and your random error is a parallax error. Now the important thing to note is the impact of systematic errors. They change the intercepts of the graph but not the gradient, whilst random errors will change the intercepts and the gradients of the graph and can also make the line of best fit difficult to plot accurately. So you can reduce systematic errors by changing your experimental technique, so like resetting the voltmeter, ensure it balances on a flat surface. But to reduce random errors, there's only one thing you can do: carry out repeats until concordant results are achieved, remove anomalies and calculate a mean. So now it's important that you can also, with a systematic error, compare the results with an expected result and subtract the actual systematic error from the result. But repeating and averaging results will only reduce random errors when anomalies are removed from results. Now you tend to find that systematic errors are discovered when certain results are taken in investigation, and you can remove systematic errors by calibrating your equipment. So what this means is you measure a known value, and if there's a difference between the measured and the known value, you can use this to correct the error. So a common example would be for a thermometer, you would say that the melting point of ice is 0 degrees. So if the thermometer doesn't measure 0 degrees when the ice melts, well at that point you can have a look at calibrating the thermometer by subtracting the difference from that particular value. Now systematic errors and random errors produce the absolute uncertainty in an investigation, along with considering the resolution of the measuring device. Now reducing systematic and random errors will reduce your absolute uncertainty in your investigation. But what do we mean by this idea of percentage and absolute uncertainty? Now in a result, you've always got to write down the numerical value of error in the experimental value. So this error will give you a range of values that the measurements must lie in. So for example, if you said that the potential difference was 10 volts plus or minus 2 volts, that means you're very confident the result lies between 8 volts, 10 minus 2, and 12 volts, 10 plus 2. So it tells you a confidence in your measured value, whilst you've got the actual value must lie within the range. Now value should always be presented in this format. Now the range of possible values takes into account the mistakes made in your experimental technique and the resolution of the measuring device used. So you can have your uncertainty as absolute uncertainty, which is a numerical value, so you could say 10 volts plus or minus 2 volts, or you could have it as a percentage uncertainty, so you could say it's 10 volts plus or minus 20%. Now every measurement has some inherent uncertainty, and the important question to ask is whether an experimenter can be confident that the true value lies within the range predicted by the uncertainty quoted. Now good experimental design will attempt to reduce the uncertainty in the outcome of an experiment. So the experimenter will design experiments and procedures that produce the least uncertainty and provide a realistic uncertainty for the outcome. So you've got to think about things like resolution of the instrument, the manufacturer's tolerance, judgments made by the experimenter, any procedures adopted, and the size of increments or the resolution of that or that's available to you. Now a combination of all the factors means that there's no hard and fast rule when calculating the actual uncertainty in a measurement, but we can think that there are 4 different methods to calculate absolute uncertainty in a value. We can assess the instrument's resolution to work out a possible uncertainty. Now again, only the experimenter can assess the other factors based on the arrangement and the use of the apparatus, and a rigorous experiment would draw the attention to these factors and take them into account. Now once the absolute uncertainty has been calculated, we can then calculate the percentage uncertainty. Now we tend to find that when questions use the term uncertainty, they refer to absolute uncertainty, and you would only calculate percentage uncertainty when a question explicitly states this. Now absolute uncertainty can only be reduced by improving your experimental technique or by carrying out repeats of your results. So let's now have a look at how you can calculate absolute uncertainty. Now, you can actually work out the absolute uncertainty in a measuring device due to how you take measurements and the resolution of the scale used. So there are two types of value you can take in a science experiment. There are readings, which are values found from a single judgment when using a piece of equipment. So you'd only look at the device once to take a reading. So an example of a reading would be measuring the mass of a beaker with a balance. You only make one judgment, you only look at it once, so therefore it's a reading. Whilst measurements are values as taken as the difference between the judgment of two values. So you're looking at a device two times will take a measurement. So, for example, when you're looking at the length of a wire with a ruler, you look at the ruler twice, once at the start, once at the end. So therefore you've made two judgments, so it is a measurement. So to clarify, a reading will only need one judgment from the experimenter, whilst measurements will need two judgments from the experimenter. Now, the uncertainty in a reading when using a particular instrument is plus or minus half of the smallest division. This is because you're only taking one value from this device. So if you think about it, let's say you want to read this value as 30 on the thermometer. Well, this would be the case. You would round something to 30 if it was between 29.5 and 30.5, because you've got no other smaller scale to use. So if it was just higher than 30, you'd round down to 30. If it was just below 30, you'd round up to 30. So this means our answer is 30 degrees plus or minus 0.5 degrees. It's half of the resolution of the measuring device. That's a very important idea. So you've got to be really understanding that as both, and now that's for a reading, but for a measurement you're taking two judgments, so two uncertainties must be included. So as both judgments have a half of the scale division uncertainty, as was stated previously with the reading, those two will both combine so that the measurement will have an uncertainty of just the division. So for example, in this case, there's an uncertainty of half a division at the top reading and the bottom reading, so you add them together, and therefore the absolute uncertainty of a measurement is going to be just the resolution of the measuring device. So we can say that the uncertainty for a reading, which is one judgment, is half of the smallest scale reading, the resolution of the device, whilst the uncertainty of a measurement, two judgments, is just the resolution of the smallest scale reading of your measuring device. So let's have a look now at our second method for calculating uncertainty. Now, there are some instances where you've got to include uncertainty due to a human experimental technique. So this will be added on to the measuring device uncertainty you calculated previously. So for example, a stopwatch might have a resolution of plus or minus 0.01 seconds. So because it's a measurement, because you're looking at the stopwatch twice, you would indicate that the uncertainty of this measurement is plus or minus 0.01 because it's the resolution of the device. But actually, in reality, you've got to consider the reaction time of the experimenter. So this must be added onto the absolute uncertainty of the measuring device to give a larger uncertainty value. So if you think the experimenter causes more uncertainty by carrying out the measurements than the device produces, you must state this uncertainty, not the measuring device uncertainty. Now, it's important to note that when you're finding a value for this uncertainty, that you can estimate this value. There's no right answer. So it can be things like fluctuating digital voltmeters and ammeters. It can be rulers not being held completely straight and parallel. There's no one right answer for you to use in this particular investigation. So that's an important concept that you've got to understand. So let's now have a look at the third method to calculate uncertainty. So we can review the third method for calculating an absolute uncertainty in a stated value given. So in this particular instance, when you're given a value in your investigation, so from like the data sheet or in a question, you assume the uncertainty to be plus or minus 1 to the last significant digit. So for example, the value of the charge on an electron as given on the data sheet is 1.6 times 10 to the minus 19 coulombs. So in this case, the uncertainty will be plus or minus 0.1 0.01 times 10 to the minus 19 coulombs. Now the uncertainty may be lower than this, but without knowing the details of the experiment and the procedure that leads to this value, there's no evidence to assume otherwise. So again, for example, if you're told in a question that the number of lines per meter is 3.5 times 10 to the 3, well, what we can therefore say is that the absolute uncertainty is 0.1 times 10 to the 3, because it's the last significant figure given in the value. Now the fourth way is to calculate uncertainty due to a variation in readings. So if you have repeated readings and then derive a mean, the absolute uncertainty can be calculated from the variation in the repeated readings. This comes from the idea that the maximum possible value for a result is the largest value of the repeated readings, and the minimum possible value for the result is the smallest value of the repeated readings. So when you look at a variation in reading, you remove any anomalous results, you then select the highest value and the lowest value, that then subtract one from the other, and that gives you the range, and then the uncertainty for this idea is then the range divided by 2. Now this happens because you're confident that the value lies between the highest value recorded and the lowest value recorded. So when the repeats are taken, the experimenter is confident that the true value is between the highest repeated value and the lowest repeated value. So what we would do is the answer we would give is the middle point between the highest and lowest values, so we can state that the absolute uncertainty is half of the range, which allows the full range to be represented when we use the symbol plus or minus. So we know that it could be up to the highest possible value, or it could be to the lowest possible value. So this method reduces absolute uncertainty because repeated readings until you gain concordance means that any anomalous results can be discarded, leaving a small range of data. So an example would be, we're confident that this answer lies between 1.8 meters and 2 meters, so therefore we said our answer would be 1.90 plus 0.10 meters. It could be anywhere between those two values. Now we can calculate the percentage uncertainty from an absolute uncertainty by doing the equation percentage uncertainty is equal to absolute uncertainty over the value times by 100, whilst if you've got repeated measurements you would work it out from your mean value. So it's the absolute uncertainty divided by the mean times by 100, where absolute uncertainty is going to be the range over 2 as stated previously. Now it's good practice to reduce your percentage uncertainty to the lowest value possible. So a way to reduce the percentage uncertainty is to use the largest values recorded possible, or to use measuring devices with a small resolution to give you a low absolute uncertainty. So here's an example of how you calculate percentage uncertainty. It's the absolute uncertainty divided by the value times by 100. Now again, the percentage uncertainty should be given to the same number of significant figures as the value, like in the example above. Now if you've got a number of different uncertainties, we can combine the uncertainties to find an overall uncertainty if we're using an equation. But there are several rules to do this. If you are subtracting or adding values in an equation, so for example its extension is stretched length minus original length, well then you've got to add the absolute uncertainties. If you've got a multiplication or a division in your equation, for example power equals potential difference times by current, or resistance equals potential difference over current, then at that point you add the percentage uncertainties. Now if you have a power in your equation, so for example area is equal to pi r squared, well what you would do is if you have a power value, you would multiply the percentage uncertainty by the power before you
to the product of 3 and 5.
Before you then add up the different values. So let's summarize our ideas. Uncertainty is a measure of how certain you are of a value. It is the range of the values you're sure the results lies in. Now the absolute uncertainty is the uncertainty expressed as a value, whilst the percentage uncertainty is expressed as a percentage of the value. So the term uncertainty refers to absolute uncertainty. Now there are 4 methods to calculate absolute uncertainty in the value: estimation due to experimental technique, uncertainty due to the resolution of the device, uncertainty due to a stated value, and uncertainty due to variations in the readings. Now you can combine uncertainties by either, if you add or subtracting values, to add the absolute uncertainties, by multiplying or dividing by adding the percentage uncertainties, and then you've got values with powers in, you multiply the percentage uncertainty by the power term. So let's now have a look at graphs. Now when you're finding the gradient of a line of best fit, you should show you're working out by drawing a triangle on the line. Now the hypotenuse of the triangle should be at least half as big as the line of best fit, and you should always draw your gradient triangle on your graph and show you're working out. So you draw a large gradient triangle on your graph, making it clear and obvious, and it should be 50% of the line of best fit. Now if you don't show your gradient triangle on your graph, then you won't receive any marks for this skill. Now the larger the gradient triangle, the more reliable the results, as more values are being considered. Now a gradient triangle can be only produced on a straight line section of a graph. But what happens if the line is curved? Well, if the line of best fit is curved, you must draw a tangent to the curve at the point that is wanted. You would then find the gradient of the tangent by drawing in your change in y and your change in x. Now remember, this only allows you to find the gradient at one instantaneous point of your line, so it's a measure of the instantaneous rate of change. Now you can determine the gradient by doing the change in y divided by the change in x. Now in this investigation, remember to show your working out and your units, and don't just write down the gradient. And remember, the units of the gradient are the units of the y-axis divided by the units of the x-axis. Now what we can do is we can use the gradient of our line and the y-intercept to determine the equation of the line, because if you've got a straight line graph, we can say y equals mx plus c, where y is the y-axis value, m is the gradient, x is the x-axis value, and c is the y-intercept. Now what you can therefore do is, if you have all of these values, you can write this out into an equation yourself and use this to work out values. Now it's important that you can work out what a gradient represents on a graph by considering the equation. So for example, if we say force equals spring constant times by extension, well, we know the equation of a line is y, the y-axis, equals m, the gradient, times by x, the x-axis, plus c, the y-intercept. So in this example, our gradient is going to be the spring constant. In this example, where F equals ma, well, if we say y equals mx, well, therefore if the y-axis is the force and the x-axis is the mass, well, then the gradient has to be the acceleration. And we can use it to even more complicated equations. So if we said that time squared equals 4 pi squared over spring constant times by the mass, well, if we say y equals mx, if y is time squared and x is the mass, well, then the gradient is 4 pi squared over the spring constant. And you can do this for just even values you've never seen before. So if we say this particular equation, we can just say y equals mx plus c. So at that point, we can take that particular equation, extrapolate it through for m and for the y-intercept, and work out values this way. So if you're given an equation, rearrange it into a form where the y-axis is the term by itself, then the term multiplied by the x-axis value is the gradient, and the term being added to the x-axis term is the y-intercept. So if we have y, m and c in an equation y equals mx plus c, we can find the x-intercept even if it's not shown on the graph, because we can find the x-intercept because if we set the y value to 0, we can then work out the value for x in the equation if we've already got m and c from the values on the graph shown. Now, to show uncertainty in your experimental values, you should draw error bars on your plots on your graph. Now, error bars are a graphical representation of the variability of data and are used on graphs to indicate error and absolute uncertainty in a measurement, and they give you a general idea of how precise a measurement is, how spread they are from their mean. So error bars are the graphical interpretation of the uncertainty we previously calculated. So it's a representation of absolute uncertainty. So error bars are a representation of the absolute uncertainty you'll have calculated previously. Now, error bars should be drawn on all experimental values you measure in AQA A-level physics on both the y and the x values. So you can see with your error bars, you'll show your highest possible values and your lowest possible values, where these values are calculated from the absolute uncertainties you've worked out previously. So the error bars are an interpretation of the range of results you're sure your answer lies in. So error bars can be used to determine if you've got any anomalous results, because at A level a result is anomalous if the line of best fit does not pass through any of the error bars of that particular value. So if the result does not have any of the line of best fit go through the error bars, it is an anomalous result. but we can also use the error bars to determine the percentage uncertainty of the value, because what you can do is from your error bars you can draw the best line of best fit and the worst line of best fit. So what you do for your best line of best fit, that's the standard line of best fit you draw on a GCSE, but your worst line of best fit is either the steepest or shallowest gradient of the line of best fit which was found from the possible data, considering your error bars, because as long as it passes through the error bars, it's a valid set of results. So you can draw your steepest or shallowest gradient with that aspect in mind, and you can understand that the percentage uncertainty is the difference in the best and worst gradients divided by the best gradient times by 100. Now this gives a result similar to the absolute uncertainty worked out mathematically, because this in theory is similar to the process of halving the range of the results to find the absolute uncertainty. So it's the same equation as one we used to work out the absolute uncertainty previously, because the absolute uncertainty is going to be the difference between the best and the worst gradients. So therefore it's going to be the difference between the two worst gradients divided by 2, or range divided by 2. Now we can also do this with our y-intercepts as well as our gradients. So we can say the absolute uncertainty is the difference between the best and the worst y-intercept drawn on the graph as shown here. So therefore our percentage uncertainty is the difference in the best and the worst y-intercept divided by the best y-intercept times by 100. And that allows us to work out the absolute uncertainty via that method as well as that. So let's now have a look at the idea of logarithms. So the logarithm of a number is the exponent to which a base must be raised to produce that number. So for example, how many 3's do we get to multiply to get to 81? So you do 3 times by 3 times by 3 times by 3, which is 3 to the power of 4, which is equal to 81. So the logarithm to base 3 of 81 is 4. So we can write the number of 3's you need to multiply to get to 81 is 4. So we say log 381 equals 4. Those things are equivalent. Now the logarithm we tend to use is logarithm base 10. So we say log 10 is just called log. So for example, log 10 10 is equal to 1, log 10 100 is equal to 2, log 10 1000 is equal to 3, log 10 to 10,000 is equal to 4, and as you can see it's working through, and you can just actually drop that subscript 10 when you're working it through. So it's a nice way to express orders of magnitude in physics. So we use logarithms when we need to consider data across many orders of magnitude. Now there's also a special case for logarithms, which is where we use the irrational number e, which is 2.718281, which is, and then it goes on forever as a base. Now when we use this base, we call it log e, which we then call the natural logarithm, and we then use the shorter notation of ln. Now there are a series of rules which are true for all logarithms, including ln, or the natural log, and base 10 logs as well, or just log. So we can say that log AB is equal to log A plus log B. That's an important idea. Or natural log AB is natural log A plus natural log B. We can say that log kx, where the two numbers are times together, is log k plus log x, or natural log kx is equal to log natural log k plus natural log x. We can say that log A over B, which is equal to log A minus log B, or natural log A over B is equal to log A minus log B. And then finally we can go through like that with log D over T, working through like that. And finally we can say log x to the power of n is n log x, or n natural log x, and we can work it through with that idea as well. So we can say that these are rules that you've got to remember, because they're not given to you in an examination, but you've got to be able to memorize and use them. Now we can use logarithms to work out values in exponential equations in physics. So for example, a charge on a capacitor. The decay of a charge on a discharging capacitor is proportional to the amount of charge left on the capacitor. So if we said Q equals Q0 e to the power minus t over RC, well, we can use logarithms to find values in this equation. When a term includes e, we can use the natural logarithm ln. So we rearrange the equation to find R, the resistance of the circuit. So what we'd do is rearrange the equation to have the exponential term by itself. So we say Q over Q0 equals e to the minus t over RC. We've got e by itself. Then what we do is we then naturally log both sides of the equation. That'll get rid of this e to the power, because when we do natural log e to the power, it just brings the power term to be a normal term in the equation. So you say natural log q over q0 equals minus t over rc. This occurs because in our definition of a natural logarithm, when you naturally log an exponential term, the exponential term becomes a standard part of the equation. We would then rearrange the equation to make the wanted term the subject product of the equation, in this case r. Now we can plot exponential equations using the natural log. So for example, y equals k e to the power minus ax. So what you can do is take natural logs of both sides to say natural log y equals natural log k e to the power minus ax. We can use our previous logarithm rule and say that actually we're multiplying two values together on the right hand side. So we can say natural log y equals natural log k plus natural log e to the power minus ax. We can then use the definition of the natural log to simplify this further and remove the e to the power by just saying it's minus ax now, because that natural log e is cancelled through, to say log y equals log x minus ax. We can say that's a y equals mx plus c equation, so we can get a nice straight line graph, and we can get our m values out, where we can say y is natural log y, minus c is log x, log k, x is x, and m is going to be minus a. So what we can therefore say is we plot log y against x. Well, y is equal to log y, x is equal to x, so the gradient is equal to minus a, which is an important idea. It's just going to be the value on the power term that's multiplied by x. And now there's our gradient there, and c is going to be natural log k again. So this allows us to work out different values. So this can be done for any equation which contains an exponential term with an e in it, and we call this a log linear graph. But you can also plot any power law as a log-log graph. So say for example y equals kx to the power of n. Well, you should take log base 10 of both sides and you'll get log y is equal to log kx to the power of n. Let's use our previous logarithm rule, because we've got two multiplications there, and say on the right hand side it equals log k plus log x to the power of n. Again, what we can do is use our previous logarithm rule, because we've got a power, it can come out as just a times on the other side, and say it's equal to log k plus n log x. Now again, we've got a y equals mx plus c graph equation here, so we can get a nice straight line equation graph where we can put log y on the y-axis, log x on the x-axis. So that would mean that the gradient of the line m is going to be equal to n, which is the power term, and log k is minus c, the y-intercept. So there we can see log y against log x, that we've got y equals log y, x equals log x, so therefore the gradient is going to be equal to the power term n, and also we can say that the y-intercept is going to be equal to log k, log the term that's times and by x to the power of n. So again, this can be done for any equation which contains an exponential term, and we call this a log-log graph. So I hope you've enjoyed this particular revision session where we've looked at the different practical skills needed for AQA A-level physics. We can assess our understanding on the different practical skills needed for AQA A-level physics, and finally understand what practical skills you need to improve upon for AQA A-level physics. So thank you very much for watching this revision session on the practical skills for physics paper 3 for AQA A-level physics. Thank you very much and have a lovely day.